Hello, I'm Seema and welcome to part 10 of the chapter Hydrocarbons. From this video onwards and in the consecutive few videos, we are going to be discussing the chemical properties of alkanes. I told you in the previous video that alkanes are not chemically reactive. Since they are saturated hydrocarbons, the valencies of all the atoms in the alkanes is satisfied. Every carbon has 4 electrons and it has got those by forming single bonds. There is no unsaturation, there is no dissatisfaction anywhere. Therefore, they do not tend to react happily. So we find that alkanes do not react with acids, they do not react with bases, they do not get oxidized, they do not get reduced, which in other words you can say as that they do not react with oxidizing agents and reducing agents. So if they react with a reducing agent, they would get oxidized. If they react with a oxidizing agent, they would get reduced. But since they do not get oxidized or reduced, they do not react with oxidizing and reducing agents. Yet, they do show certain kinds of reactions. And there are 7 of these reactions that have been listed and that are there in your syllabus. The first kind of reaction that alkanes show are substitution reactions, which we will be doing in this video. Then the second type of reaction would be combustion. Third is controlled oxidation. Fourth is isomerization. Fifth is reaction with steam. And sixth is aromatization. And seventh is pyrolysis. So we'll be doing all of these kinds of chemical reactions in the or chemical properties in these few videos. So let us start with substitution reactions in the case of alkanes. How do substitution reactions take place in alkanes? As I told you that they do not get oxidized or reduced. The simplest definition of oxidation and reduction would be the gain of oxygen and hydrogen. They do not gain atoms. So if they cannot gain atoms because they are already saturated, there could be an exchange. You know, when you climb up a bus that has been that has all the seats occupied. Imagine a scenario that all the seats are occupied in a bus when an old man gets up on the bus. And when he comes in and he finds that all seats are occupied by youngsters. Now, he cannot take a seat because there is no available seat for him. Yet, one of the youngsters may willingly get up in order to give more stability to the old man, because he can stand and he can balance himself while it would be difficult for the old person to do it. So he stands up and he gives the old person his place. So a substitution, that seat which was already occupied by one person is being occupied by another person. So there is a substitution. It has been substituted by another person. That is possible. You may not add atoms, but substitution is possible. So such reactions in which the hydrogens that are present in the alkanes, they are substituted by other atoms or groups of atoms. They are known as substitution reactions. So substitution reactions do take place, and what kind of substitutions are seen in the case of alkanes? In the case of alkanes, we find that they get substituted by halogens. They can get nitration can take place and sulfonation can take place. So nitration and sulfonation do not take place for lower alkanes. They usually take place for higher alkanes. So they are not, they would be important, but only for higher alkanes. While halogenation is something that can take place for all alkanes. And we would be studying, the example that we would be taking and studying would be halogenation. How does the substitution of a halogen atom take place in an alkane? Halogenation usually takes place at high temperatures. That is, it takes place between 573 to 773 Kelvin. Or if you cannot provide that kind of a temperature, then halogenation can also take place in the presence of sunlight or ultraviolet light. Actually, it takes place in the presence of ultraviolet light, since sunlight also has ultraviolet light. Therefore, it can take place in the presence of sunlight too. So you would say it could either take place at a high temperature, or it could take place in the presence of ultraviolet light or sunlight. And as I told you, that lower alkanes do not undergo nitration and sulfonation. So in the case of halogenation, let us take the example of chlorination. And chlorination of the simplest hydrocarbon, that is methane. It is important to understand how this process takes place, because when substitution takes place, you know, in an alkane there are different hydrogens which are attached to the carbon atoms. So which hydrogen, and since alkanes are saturated, all these hydrogens, they seem to be identical. Now the halogen can substitute different hydrogens, and the halogen atoms could substitute more than one hydrogen. So you get multiple products. And that is why it is important and interesting to see how this takes place. So we take the example of chlorination of methane and see what happens. When methane reacts with chlorine in the presence of H nu represents light. So light can be ultraviolet light, it can be sunlight. In the presence of sunlight or in the presence of photon, which is in the ultraviolet region. So methane reacts with chlorine to give you one substitution. One chlorine takes its place to form methyl chloride or chloromethane, CH3Cl. So one of the hydrogens has been substituted and you get HCl. That hydrogen which has been substituted combines with the remaining molecule of the chlorine. That is, the two chlorines, they part and they give you two chlorine atoms. One combines to give you CH3Cl, and the hydrogen whose place it takes, that hydrogen combines with the other chlorine to form HCl. Now, this CH3Cl that is formed is in the reaction mixture. It doesn't just sit there, it still has hydrogens which can be replaced by chlorine. So, in the presence of the light which was already there in the mixture, this methyl chloride then further gets chlorinated to give you dichloromethane. That is CH2Cl2. Another hydrogen atom is substituted by chlorine. It doesn't stop here. There are still two more hydrogens that can be substituted. So in the next step, you have dichloromethane reacting with chlorine in the presence of the light which was already there in the mixture, and you have like in the presence, ultraviolet light was already being given to this reaction, and that results in the formation of chloroform, that is CHCl3 or trichloromethane. And HCl is formed. Now you still have one hydrogen, so that is also replaced. So CHCl3, that is chloroform, reacts with chlorine to give you carbon tetrachloride, and HCl is produced. So this is interesting. We find that all the hydrogens of methane will be substituted one by chlorine. So you started with methane and chlorine, but you end up with, when you see the products of the reaction, you will find that you don't start with one molecule. Some of the molecules would be methyl chloride, some would be dichloromethanes, some would be trichloromethanes, and some would be carbon tetrachloride. So you get a mixture of hydrocarbons there. Similarly, if we started with ethane, ethane would also combine with chlorine to give you CH3, CH2Cl. That is, we show the first substitution. One of the hydrogens of the alkane is removed and it combines with the other atom of chlorine, and that one atom of chlorine attaches it to the alkane, resulting in the halogen substituted or chlorine substituted alkane. And of course, here also you will get multiple compounds. It has been seen now that the rate at which this displacement takes place or the substitution takes place is different for different halogens. Fluorine is the strongest, is the most electronegative halogen. Therefore, fluorination takes place really fast. Then comes chlorination, then is the rate of bromination, and iodination has the lowest rate, right? So, because iodine is a larger atom, it is not as electronegative. So, electronegativity and size of atom shows that fluorination would be a kind of an instantaneous, very quick reaction. And chlorination and bromination are more, moderate. And that is why most of the properties that we would be studying would be of chlorine and bromine, because iodine would be too lazy, too fat, and fluorine is hyperactive. We don't want both extremes. So most of the reactions that we would be studying would be chlorination and bromination. So that is the rate of replacement. Now, the hydrogen in the alkane, if it is a branched chain alkane, you may have hydrogens that may be attached to a tertiary carbon atom, they may be attached to a secondary carbon atom or a primary carbon atom. So it has been seen that the tertiary hydrogen, the hydrogen which is attached to a tertiary carbon, would be replaced first. And if you have a branched chain hydrocarbon. But if you have an open chain hydrocarbon, even then the primaries are at the ends, those would get replaced first, those hydrogens, and then the hydrogens of the other carbon atoms would get replaced. So we find that the rate of replacement of hydrogens is a tertiary hydrogen. Hydrogen is not tertiary, it is hydrogen which is attached to a tertiary carbon would be replaced first, then the secondary, and then the primary. That is the rate at which this replacement or substitution would take place. As I told you, iodine is large in size. It is less electronegative in comparison to the other halogens. Therefore, iodination is usually slow and it has to take place in the presence of an oxidizing agent. This is not going to run the race easily. It has to be pushed even to participate. So even to participate, this reaction would be slow and it would not be spontaneous. It would have to be done in the presence of an oxidizing agent in addition to the sunlight or ultraviolet light. So an oxidizing agent like HiO3 or HNO3. Why? What does HiO3 or HNO3 do in this case? When methane reacts with iodine, or we are carrying out the iodination takes place just as this happens. That CH3I is produced and HI is produced. But this is a reversible reaction because this is not very stable, since this did not as it is react very happily. So the difference between the stability was not much. These products that are formed are stable. They are stable as long as they are not, they are not facing more chlorine and more light. Then they would be unstable as long as they keep getting the light and they are in the presence of chlorine. But in the case of iodine, it's not happily reacting. It is a reversible. It would try to go back to form the original reactants. So we don't want that. If we want to carry out the iodination, what will we do? We will carry out this process, but the CH3I produced and the HI produced, that has to be, if we can somehow separate these two, if we can remove one of the products from the reaction mixture, then there is no possibility for them to react back and give us back the reactants. So since it is a reversible reaction, what we do is we add HiO3, an oxidizing agent, which then reacts with the HI and blocks it. How? It reacts with HI, being an oxidizing agent, it oxidizes HI to iodine. Hydrogen is removed from HI. So it oxidizes it to iodine and water is formed, and therefore the HI that was produced is removed from the reaction mixture. So it is not possible for it to react back and give us back the methane and iodine. So that is how you would carry out the iodination of methane. Now, what is the mechanism? How does the chlorination take place? What are the steps? The process of chlorination or chlorination takes place by free radical mechanism. The intermediate that is formed in an organic reaction in this case is a free radical, and therefore it is known as the free radical mechanism. Free radical mechanism, or in this mechanism, when a reaction follows this mechanism, it follows three steps. The first step is known as initiation. Initiation means that it is free radical mechanism. So free radicals have to be initiated, have to be created. So unless there are free radicals in the reaction mixture, free radical mechanism cannot be followed. So the first step would be that free radicals are created. So that is known as the first step, that is initiation step. The second step is, it is a kind of a chain reaction. In the second step, these free radicals are going to carry out the reaction. And the reaction is being carried out in such a way that more free radicals are generated and they are used back, more are generated, used back, more, and till the entire reaction mixture keeps reacting, or almost as much as possible. And then comes the third step. It involves a third step. And what happens in the third step is that these free radicals that are formed during the first and the second step, sometimes they combine with each other. And they combine with each other and result in the formation of a product that does not give rise to a new free radical. So if a new free radical is not formed, the reaction it stops there. Because for this reaction to take place, for the chain to continue, the free radicals should keep on being generated. So when the free radical is not formed, it is blocked by forming a bond with something and it becomes a stable compound, then the reaction stops. That is why this third step, where the reaction stops as a result of the free radicals being blocked, is known as the termination step. So free radical mechanism involves 3 steps: initiation, propagation, and termination. So let us understand these in terms of chlorination of methane. The first step is initiation. In initiation, free radicals are formed. The chlorine molecule, which is the chlorination that is taking place, the chlorine molecule actually, in the presence of light, undergoes homolysis. What is homolysis? Lysis means breaking, the bond breaks. Homo means same. So homolysis, the breaking of the bond takes place in such a way that both the atoms get 1 electron each. Usually when ions are formed, what happens when a bond breaks? One atom takes both the electrons of the bond. That becomes negatively charged. And the one that lost its electron becomes positively charged. That is how ionization takes place. That is heterolysis. But in homolysis, the bond breaks and both the atoms get back their electron. But now they are not satisfied. The octet is not complete. And that 1 electron is kind of dangling and waiting to react with something and complete its octet. Such species are intermediates and they are known as free radicals. So homolysis takes place and both the chlorines, they form free radicals. These free radicals is an intermediate state. It is not stable. It is not going to stay like that. The moment free radical is formed, it starts acting to satisfy its valency, which can be done by reacting. So since chlorine is more electronegative than hydrogen, it will go to the alkane, that is methane in this case, and it will replace the hydrogen. It can take the place of hydrogen. So it forces hydrogen to come out of the molecule and the chlorine free radical takes the place of that hydrogen. So what happens in the propagation, that does not take place in one step. This also involves steps. So in the second step, that is in propagation, what happens now? This free radical that was formed comes and attacks the methane molecule. And chlorine, being more electronegative, it pulls the hydrogen towards itself. One of the hydrogens comes here and results in the formation of HCl, and this methyl, the methane that was there, it turns into the methyl free radical. The carbon now has got its electron and the chlorine has left, and therefore the free radical, that extra dangling electron, comes over on the methyl free radical. Now this methyl free radical further combines with the chlorine molecule, and since this is a free radical, one free radical should be there. So we found that in the first step free radicals were formed, the chlorine free radicals, but here in propagation step the free radical only changed we still get a free radical as a result of this step. And this free radical further reacts with the neutral molecule of chlorine, and it results in the formation of methyl chloride, and again homolysis takes place here, and the chlorine here, chlorine in this case, homolysis actually doesn't take place here. Both the electrons go to this, and therefore this chlorine gets deficient in its electron and it turns into a free radical. Then this free radical further combines with methyl chloride, that is the methyl chloride which is formed, or you could say not this free radical, you could say the second free radical. It is just there is no identification which chlorine free radical is going to react. So one of the chlorine free radical then further reacts with CH3Cl, results in the formation of CH2Cl free radical, and HCl is formed. Now when this happens, this one will further react with another chlorine molecule, result in the formation of CH2Cl2, and Cl free radical is generated again. Then the first step starts again. This free radical attacks this CH2Cl2 that is formed and results in the formation of CHCl2 free radical, and one hydrogen is removed to form the HCl, and this becomes the new free radical. Now this has an empty space due to that dangling electron, and chlorine takes the place of that in the next step again. So this now reacts with the chlorine molecule, results in the formation of the Cl takes its place, and this chlorine becomes a free radical. So free radical is generated again. Now this free radical further reacts with the product and generates the next free radical, and this continues until all the hydrogens of the methane molecule are replaced by chlorine. So we see a chain has started. A free radical was formed, it reacted, resulted in the formation of another molecule which was a free radical, that reacted with the molecule, resulted in the generation of a free radical. So in the propagation step, we see that in every step a free radical is created. So initially it was as if, you are in a cycle stand, there are many cycles. You go and the first cycle, they are all standing parallelly to each other. And you go and stand on one side in front of the first cycle, and all you have to do is give it a little nudge. All you did was you created one little motion, and that cycle falls on the next, that falls on the next, that falls on the next, and all the cycles in the stand fall down. Right? So it is like that. Once in the initiation step the free radical was created, that pushed the next one, that created the next free radical, that pushed the next one, next, and the reaction starts like a chain. And that is what a propagation of a chain is, that it continues one, next step, and in every step a free radical is created. Then how does the reaction stop? What will happen in this? Will this continue forever till all the hydrogens are replaced? That doesn't usually happen. What happens is that there are free radicals don't know that that's the reason why we got so many products. Because they don't know who they are reacting with. And we did not start with one molecule of methane, we started with millions of molecules. So all these reactions are going on in the mixture. And what happens, sometimes two free radicals, they come and hit each other. And both of them are looking for one electron to complete their octet. So they immediately form a bond with each other. For example, when two chlorine free radicals come and bump into each other, they result in the formation of chlorine molecule. Two methyl free radicals come and bump into each other, they join up and form a bond and results in the formation of ethane also. Then methyl and chlorine free radicals bump into each other, both the free radicals were there, and they result in the formation of methyl chloride. So we find that in these reactions there is no new free radical formed. Since there is no new free radical formed, it cannot continue the reaction. In all of these cases, in every step a free radical was being formed, which helped in the next step. So this is kind of resulting in the stopping of the reaction. As the free radicals keep combining with each other, those molecules get blocked. They are no longer supplying free radicals for the propagation of the reaction. So when all free radicals kind of combine with each other or result in the propagation and give us the products, in the end we get a mixture of products. And the mixture of products would have all of these products in the reaction mixture. So that is how halogenation or substitution reactions in alkanes take place. So with this, I'll wind up today's video. If you found it helpful, give it a thumbs up, subscribe to my channel, recommend it to your friends, and please keep returning for more videos in chemistry. Thank you for watching, and bye-bye for now.